Welcome to qnawire.
We need to find the angular momentum of this disk, knowing that there's angular velocities that make the disk rotate in this direction and also make it rotate in this direction. So to solve this problem, we're going to need to find moments of inertia across the x-axis, y-axis, and also the z-axis. And we're going to use the formula that the angular momentum h is going to be equal to the moment of inertia I times the angular velocity omega. And we're going to do this for the x-axis, y-axis, and the z-axis. So we're going to start by finding the moments of inertia across each axis. So for a thin disk, we know that the moment of inertia in the x direction is going to be equal to 1 over 4 times the mass of the disk and the radius of the disk squared. And this is also true for the moment of inertia in the y direction. And then for the moment of inertia in the z direction, we know that that's going to be equal to 1 over 2 times the mass m times the radius r squared. And we're given angular velocities of the disk. And using the right-hand rule, we can determine that the angular velocity in the x direction is equal to 0. The angular velocity in the y direction is equal to omega 2. And the angular velocity in the z direction is equal to omega 1. So we can now write out the different components for the angular momentum. So for the x direction, this is going to be equal to the moment of inertia in the x direction times the angular velocity in the x direction. And we already know that there's no angular velocity in the x direction, since by the right-hand rule, we can determine that that velocity is going to be 0. So we can say that h of x is equal to I of x, which was 1 over 4 times mr squared times 0. Thus, we can say that the x component of the angular momentum is going to be equal to 0. So we're now going to find the angular momentum in the y direction. And we plug in the values that we calculated here. So we'll get that h of y is equal to the moment of inertia in the y direction times the angular velocity, which we know is omega 2. And I will find the last component in the z direction. And we found that the moment of inertia in the z direction is 1 over 2 times mr squared times omega 1. So in terms of a vector, we now have the I component, the j component, and the k component of the vector of the angular momentum about the disk. So now we can say that this angular momentum h of g is equal to the x component I plus the y component j plus the z component k. So now the final angular momentum is equal to 0I plus 1 over 4 mr squared omega 2 j plus 1 over 2 mr squared omega 1 k. And this is the angular momentum across the disk.